Hello everybody, let us start today's lecture, and today we are going to discuss some unsupervised methods which are slightly different from what we have studied so far, but I will explain everything as we go. I will use some existing presentation for this lecture. It's not exactly lecture number 8, and I will also show some of my own examples as well in the process. And there will also be available this video record, which you can then study again. So let's start discussing the unsupervised learning method. So whatever we have discussed so far, either neural network, random forest, decision trees, all that stuff, yes, was belonging to the supervised methods. Where, well, all those methods we have discussed so far, starting with the regression tasks, that's linear, logistic, yes, neural networks, and other support vector machines, decision trees, yes, all of that stuff. Although some of these methods actually can be used in unsupervised mode as well, for example, neural networks, which we will cover in this course too. But mainly, we have considered this task as supervised problems. Supervised problems task was to train a model of any kind, either regression or neural network, considering inputs of X training data and Y training data. That is for supervised methods. And because of that, this model was using specific cost function which used Y data and X data, and it predicted some Y predicted values. Then, if you want to, you can validate this model by feeding the test data and predicting Y predictions, yes? Then, without specifying this Y test data to the model, yes, it doesn't go here, as you can see, you then make, let's say, accuracy estimate, or stuff like this, or precision, or any other metrics for that matter. That's how it was working in supervised methods. In unsupervised methods, you start right away without specifying even training data, yes? So you have a model, likewise, which you would like to train, but either you don't want to, or you don't even have, you can only provide X training data, and there is no Y training. And it has to make the predictions based only on that. And not only make predictions, it also has to learn to make the correct predictions itself, yes? Then, if you happen to have this data, again, you can use that to estimate the performance by calculating some metrics. That's how you can decide if it's doing predictions correctly or not. But in either way, you do not feed this data to the model, yes? It doesn't know any inputs of your, well, actual score, actual predictions, forecasts, or classes, or whatever we are using. So today we are going to discuss k-means clustering algorithm and db-scan clustering algorithm, as well as we will cover matrix factorization with some example on Netflix, yes, and discuss some performance issues, yes. Then we will go to computer class with one of the groups to make the practical exercise specifically on k-means clustering and db-scan, where you will be able to compare these two methods and see why we do need different methods, yes. For example, why k-means cannot solve specific types of problems, but db-scan solves that problem much better. So again, this is short, brief repeating, yes, that supervised machine learning algorithms could be classified into regression tasks and classification tasks, where classification task has limited number of outputs, labels, yes, like classes, cats, dogs, handwritten digits, etc. regression has continuous output, yes, so that doesn't have to be split into specific number of possible cases. And then there are unsupervised machine learning methods, which we can split into clustering problems, yes, when you have limited number of these clusters, or if your outcome is continuous, yes, that means you need some kind of prediction, yes. Let's say, for example, what you want to try to do is to make the prediction. Well, let's take the Bitcoin, for example, yes. You have some data right now, yes, how this Bitcoin is performing, which is, by the way, non-stationary, yes. One of the groups already knows what it is, another will find out next week. Meaning that it's quite difficult to actually predict what is going to be in future. Nevertheless, we want to train a model being able to use this history to tell you what this Bitcoin price is going to be next year, for example. Solely based only on the existing data. So this is also some kind of forecasting, the prediction, but we don't really have to, well, we don't really know what it's actually going to be next year, because next year is not here yet. Yes, it will be in future, and once it hits, we will find out what is the real price, then we will see if it works or not. Yes, and there we can use other algorithms such as matrix factorization, Kalman filtering, which is specifically used a lot signal processing in telecoms, and unsupervised neural networks, which is some adaptation of neural networks we know to solving unsupervised problems. So let's see some examples of what kinds of problems can we solve by using unsupervised machine learning. So let's say you have a lot of data set, our handwritten digits, yes, which we know and which we have used, and which we will also try to use in one of our next practical exercises, not today, I'm afraid, but next time. So let's say you have a lot of digits and you don't even know what is shown where. So you only literally have these photos and nothing else. And you don't really want to sit there and check, let's say, 1 million of these photos and manually say, okay, I see here that it is 1. So label is 1. You take the next photo, then you open your text file and say this is 2, and so on. So what we want to do now is more likely like split all the photos in pictures of 1, pictures of 2, pictures of 3, and then you try to see whether accidentally some picture of 2 happen to be in cluster of pictures 1, which is much faster for you, because you can say every picture is picture 1 except those I can see that are not. Yes? So you only literally have to check that there are no wrong pictures belonging in this cluster, which will solve your problem. Another type of problem you can solve is what are the top 20 topics? Well, it's now no longer Twitter. Yes, it's X, I believe, network. Yes, right now, specifically right now. In future, they change, of course. Yes, and also how many distinct accents are for people at specific city, for example, or specific country, or specific region, or whatever, yes? So here are some, not full, but short list of methods we have discussed so far, yes? And today we are going to focus on clustering and matrix factorization, but as I said, there are also something called hidden Markov models, which again we will not cover during this course, but we will specifically explain some differences happening to the neural network, what needs to be changed in neural network so that you can use them from supervised learning in the unsupervised learning. So some things you need to change. Well, some kind of a spoiler is that you have to change a cost function, obviously, yes, because that considers your inputs. So that's probably going to be it, but there are some other factors to consider. Another example is if you have, let's say, some kind of a picture, yes, showing some kind of an object, I don't know what kind of object, let's say some coin, yes, And then you want to find inside of this picture specifically where exactly that coin is located. Yes, so this is called a segmentation. Then we can try to do some compression of the data because, well, handwritten digits, as you will see later, can easily be compressed into much compact way. And studying some underlying processes, yes, like how exactly your place of birth affects your accent, yes, and stuff like that. So here is the example of the type of the problem that we are going to try today in the practical exercise as well, having certain clusters of certain data. Some of the data points are green, some of the data points are blue, and some of the data points are red. And what we want to do is, initially, you are giving this data without color. So all of the points, let's say, are going to be, I don't know, let's say black color. And then you have to split them into groups by specifying certain regions. Yes, so in a sense, you can basically say that, okay, we can have here certain regions like region 1, region 2, and region 3. And any point that belongs to a certain region, with high probability, we cannot say certainly, yes, is going to be of this specific cluster. But as you can see here are some red points in the blue region. There is also a red point in the green region, and also some blue points in the red region. So these take some, I don't know how to say, these boundaries, yes, these regions are not going to be like straight lines. They will have much more complex shape, yes. Another kind of problem is like this. When you have some picture, you can see some person there holding something in his hand, yes, some background there with different kinds of pixels, yes. And for this kind of problem, we are going to need some other algorithms which will work differently from the algorithms that work with this kind of data, yes? So we have only 2 dimensions here, but you can imagine that we can have as many dimensions as you'd like to, where each dimension from our data set comes as a one separate column. So let's say you have some data, X, yes, where you have age, that is one dimension, where you have, I don't know, job, another dimension, where you have income, the third dimension, if it is a student or not, fourth dimensions, and so on. So each column of your data set is one dimension. And this is preferred for us just because we can visualize it. Of course, you cannot really visualize if you have like 10 columns in your table easily, but don't worry, we'll speak of that as well, like to how can we convert 10-dimensional data into, let's say, 3-dimensional, which then you can try to visualize actually. Now, what we need to understand here is that our brains specifically work in such a way that we see clusters where they might not necessarily be actually there, yes? Unlike the artificial intelligence algorithms, which do not overthink it as we people do. So obviously we can group some animals into categories, like dogs into one category, cats into another categories, but it's not really the case how it was designed in the nature, yes? So the easiest example about that is constellation on the night sky, yes, because nobody was specifically putting all those stars in specific places so that they form these constellations. It's our imagination that has created it, but otherwise they are just some random points in the space, yes, and the people's nature is such that they try to find some patterns, some categories, some mathematical, I don't know, laws, yes, where actually there might not even be ones, yes. Now, that is different for artificial intelligence models, yes, for machine learning algorithms. And we can see from this example that actually there are no really clusters, yes, here. We cannot say that this is where one cluster ends and another cluster starts. Normally, this is more like a transition, natural process, like Some points might even belong to multiple clusters in reality, yes? But, well, we still have to somehow make our models, we still have to consider that, and there are multiple ways for that to happen, yes? So the main issue is that sometimes we use this clustering unnecessarily, yes, more than it has to be done, because we consider that our data can be split into clusters. Sometimes it doesn't work and you don't understand why. Well, the reason might be very simple, because actually your data might not be clusterable, yes? And as I said, in reality, just like with a rainbow, there are no specific, like when your red color ends and orange color starts. There is this gradient, this transition, like your red color gradually becomes orange, your orange color gradually becomes yellow, with billions of different color variations, yes? So, but either way, let's consider that we can still split some of the problems, because some of the problems obviously can be categorized, obviously can be split into categories, and for these kinds of problems we can use clustering, yes? So let's say like email clustering, yes, work email, spam email, some, I don't know, bills, promotions, yes, whatever else. Then another kinds of problems. So there can be different ways of clustering. First of all, you can have separate clusters, like here, for example, yes, where each of the clusters is independent from any others and is not belonging to any larger cluster. But you can also have somewhat called hierarchical structure of the clusters. So let's say you have one big cluster, another big cluster, and another big cluster, and inside of these big clusters you also have smaller clusters, like so. Yes? So this is a hierarchical clustering structure. So some of the problems are this kind, some of the problems are not this kind. I don't know, like grouping news based on the topic sports, politics, etc., etc., and then accordingly into smaller categories. Now another important thing is that there can be hard clustering when, let's say, you have certain points of different color, and each of the points can belong only to a single cluster. Or there can be soft clustering, where you are not specifically sure about which of these clusters this point is belonging, and say that it can belong to one cluster with this probability and to another cluster accordingly with this probability. So I do have actually quite a good example of this kind of soft clustering. So for that, let me take 5 minutes of your time to explain some very basics of the telecom theory, yes, of data transmission for digital communications. So as you probably know, to no surprise, that we send in our digital communications data as bits of information, either 1 or zeros. Yes, so basically, let's say, corresponding to certain voltage levels, 0 volts or 5 volts, yes, as a signal, electrical signal. Then we can say our system's goal is to transmit these ones and zeros, and sometimes we tend to group and send them in batches, not like a separate 1 and separate 0, but groups of them. For simplicity case, let's take the batch of 2 and let's make a map, yes, so that's how it's called, also a constellation map, by the way, in telecom theory, in a complex plane. So you have a real axis, you have imaginary axis of 4 points, 1, 2, 3, and 4. Each of these points transmits 2 possible bits. So let's say 0, 0, 0, 1, 1, 1, and 1, 0. So this is our abstract map that we have created and use as a model. To this abstract map, we assign some real signals. So let's say, for example, that here we will assign plus sine wave of the specific frequency and time.
Here, let's say we will assign a plus cosine wave. Here, let it be minus cosine, and here let it be minus sine wave. So real measurable signals are assigned to these abstract constellation points. And what happens in the channel is when you transmit your data, say here is your base station, here is your mobile device, and your signal is being transmitted in the form of this trigonometrical signal, is that just like with the voice, when you, let's say, climb some mountain, shout as loud as you can, but still at certain distance your voice volume is going to fade gradually until nobody can hear you. The same happens to this signal. It loses its energy as it's propagating. Yeah, so we can say that its energy is losing. And this is a problem because in addition to our signals, there is always a noise around us, yes? And this noise is very weak, yes? It doesn't pose any problem if you are here at the base station. But as you go further and further from base station, your signal weakens, and that's when noise starts to kick in, yes? Because of this noise, the point that you have originally transmitted, like here, for example, that was your original data, you have transmitted 2 zeros. Because of the noise, it moves slightly to this certain other point. Instead of that, what we receive is something like this, or something like this, or even something like this. Yes? Now, this distance, how far it can go off, is distributed by probability in according to the normal distribution. Yes? So that is the noise distribution. So that means for us that having this noise is high probability, having this noise is low probability. Yes? Nevertheless, the algorithm that we are using to detect this signal works in a very simple and obvious manner. So let's say you have received this point, and now you try to consider what you have actually received. 2 binary digits, 0, 0, 0, 1, 1, 1, or 1, 0. So the algorithm is going to calculate the Euclidean metric to this signal, to this signal, to this signal, and this signal, and choose whichever is the minimum of these metrics. That's how it makes decision. As you can see in this case, it's going to make an error because originally you transmitted 0, 0, but your received point is closer to 0, 1, and that's how the error happens. So this is a hard clustering. In reality, yes, and we can also make some algorithms more advanced, and in fact using machine learning as well. So real axis and imaginary axis, and with our original points, that here you have certain regions overlapping, yes? So in reality, your clusters are somewhat overlapping. Yes? And your received point, let's say here, can have different probabilities. Probability 1 to belonging to the point 1, probability 2 to belonging to point 2, probability 3 to belonging to point 3, etc. That is called soft clustering. Yes, when you only estimate how probable it is that this point belongs to the specific cluster. So let's go further. And the first algorithm we are going to discuss is specifically calculating this Euclidean distance, just like the detection of the radio signals I have discussed with you right now. Somewhat differently, however, because in radio signals we actually know the original points that we should receive. In many problems here in clustering, we don't really know what is your center of the cluster. Yes? So here we actually have to know how many clusters are there and what is the center of each cluster. But once you make some assumptions, so let's say I will say there are 3 clusters and I pick some points either randomly or by using certain smart approach, yes, to actually decide what points are belonging to each cluster. So this is quite simple algorithm, which we will even discuss right now how exactly it works. That is considered to be a greedy in the sense that it's not really perfect, not really optimal, but it's somewhat efficient, yes. And its operation is quite simple. So first of all, if you have some data set, so let's say here, yes, some data set, no, here, yes, then in each of these different color clusters, you choose one of the points as the centroid of that cluster. Of course, at the beginning, you don't really know that this cluster starts here and here, etc., etc. You have to assume something. So it is a good idea to actually choose these centroid points as far away from each other as possible. Yes, so we do want to have them spread around your data points. Now we can either choose them randomly or let's say try to optimize some distance-wise, how far are they. We don't also want to use it too far from the edge of this total data amount, so somehow we have to choose these clusters. Now once you have chosen these points, yes, what is going to happen next is that you estimate the distance of each of these different points to each of these centers. Yes, so for example here you estimate this distance and can see that actually borderline goes here after this point. The lower distance belongs to red one rather than teal one. Yes, so that is actually quite simple. So let's say you have these centroids. Now you have some points for which you need to decide to which cluster are we going to put this point. So for example, so you calculate Euclidean distance towards all of these clusters and choose the minimum one. So this point belongs to this cluster then. Same wise goes for the next one. Yes, so let's say for example this point. Again, you calculate distance and evaluate to which cluster it belongs. So let's say again it belongs to this one. So this way you go through all of the points you have, you calculate distance from each centroid to each point, yes, and group them based on the minimum distances. After that, what you have to do is to, once you have it like this is your first iteration. It's not best, of course, it's just what happens to be your first step. And after this step, now having these clusters, you can find the geometrical center again for this cluster. Now it's going to be here. So you update your centroid and go through another iteration. So here in this picture you can see these old centroids as yellow crosses and the new centroids which you calculate from the cluster as blue dots. Yes, and this way actually you can, after you have updated these plots, continue this operation until it happens to be that your centroids do not update anymore. It's difficult to see here, but there are yellow crosses and blue dots on this picture. They are just the same point, yes? Like here maybe you can see, yes? So when that happens, you know that further improvements is impossible, yes? So that is your final solution where you can stop because it's not improving any further. That's basically the idea. Yes, you randomly pick starting centers, you assign all of the points into the clusters based on how far are they from the centers, then you update your centers and repeat until your centroid updates are no longer going to move. Yes, that's basically all the idea of this algorithm, as simple as it is. Yes, you can even program it yourself if you want to. Now, the question is, the main question is, how are we supposed to start? Because the outcome, the result of your prediction is going to vary very much depending on your initial points, how you have selected your original centroids. Not to mention that actually you have to know in advance how many of the centroid points are there. So when we will program our exercise today, you will see that you have to specify, I am going to need, let's say, 3 or 4 or 5 clusters. So that is the input to algorithm you have to know. Yes, you can of course guess it. You can of course try to change it because sometimes you may not be sure how many categories are there. So you can try different approaches and see which works better. But still, first problem is you need to know how many clusters are there. Second, you need to find some starting points, preferably not too much from the edge and also not too much close to the center of this pattern, somewhere in the middle, and also all of these points have to be spread widely one from another. Yes, so either you choose randomly, but random is random as you imagine. You may even choose 2 points that are nearby if you are unlucky. Yes, and another approach, more smart one, is using k-means plus, which iteratively constructs also random sample, but it also evaluates the distances between all these centroids. Yes. Now, here we need to mention that optimal k-means clustering is considers something to be non-polynomial, or how that wasn't spelled, yes, and be hard problem, yes. Well, this is about computational efficiency, speed, etc., yes, sufficient to understand that this means that it's computationally intensive and difficult problem to solve. So for that, we actually do something called randomization and approximation. Yes, so that's why we do have to do some randomizing. We cannot really, especially if we have millions of these data points, find optimal centroids easily. Yes, well, technically that would be probably possible, but it would only be working for this particular data. If you change your data set, you will have to start over from the zero again. And that is the problem. There is no universal solution here. Now, the idea how exactly this k-means plus works is quite simple. Yes, so basically, first we choose random points. Yes, that is the beginning, just like here. But then we actually, for every remaining point that you haven't chosen, we calculate the distance and choose the out of these remaining points randomly, yes, a new cluster center based on the distance. Yes, so probability will be depending on how far is your point. So the further is the new centroid point from your original centroid point, the higher will be probability that you are actually going to choose that one. So this way you actually can optimally distribute them and then start working on this algorithm. Now, there are many variations of this algorithm as well, such as fixed size clusters or generation of M-best soft clustering algorithms, but we are going to try the very basic one in the practical exercise to deal with some data set. Now, what is also quite interesting to notice and maybe to discuss is how can you be sure that there are actually 3 clusters here? Maybe, just maybe, there are 4 of them. Or maybe we can say there are 2 of them. Maybe this one is red cluster and maybe this one is green cluster. So answering this question also is not like straightforward and easy, but at least we have something called AIC information criterion. Yes, so this AIC, yes, can help you to find the optimum number of clusters, both from the perspective of how accurately they work and how complex is your model. Yes, so it favors, well, tries to minimize the number of clusters to achieve the higher, well, we can say separatability of these clusters. So, of course, you can't say, okay, I'm just going to say I will have like 1,000 clusters here. They will be very, very small, very separatable, but will that be good grouping? Not really, because obviously here we see some pattern. And this is a cluster separate from this cluster because of its density. So here you can see there's one density, here you can see density is much lower. Yeah, so basically it's not only about shape of the cluster, it's also about how much points are in this shape. So green and blue ones are dense clusters, red one is not so dense cluster. So this archaic criterion can actually help you to evaluate, if you don't know how many clusters do you need in your specific problem, to actually determine that. So let's see now another algorithm called dbScan. So this is a density-based algorithm, so that stands for the first two letters. Now the problem with k-means algorithm is that it's very, very well suited for these spherical clusters, for these circle type clusters like we have seen here. Or maybe even here, yes. You can consider each of these clusters to be certain sphere around the centroid, yes. Like this one, like this one, like this one, etc., etc. So that's just how k-means actually works. It's its nature, it's basics, yes. And in case you have some data not following this regular shape, like in this picture here, it's obviously more complex shape, yes. Some of this is silhouette of person, some of this is some background, something he holds in hand, yes. Or in the Netflix dataset, so this is Netflix dataset about movies, about ratings, and all that stuff, yes. Now, this is much more closer to real data, and that's where you will see that surprisingly your k-means algorithm is not so good anymore, yes, and we need some other algorithms for that kind of problem, where density-based algorithm actually comes to our help. Now let's also consider how exactly density-based algorithm works. Yes, so the key point, as it stands from the name, yes, is that it considers how dense points are. So that means that you need to specify a certain, how it's called, diameter of the range called epsilon, in which you are going to evaluate how many cluster points do you have. So for this blue circle line, in this range epsilon, we only have one blue point. Well, we don't even know if it's blue, if it's red or yellow, yes, so we just know that within this range of epsilon from this point, there are no neighbors, yes, zero neighbors. Now for this one, if we choose this point as a base, then within this range you can see there are 3 neighbor points, yes? Now, in order to say if all of these 4 points together with the one you have selected and 3 neighbors are belonging to the same cluster or not, you need to specify minimum number of points for this sphere to be considered as the same cluster. So let's say it is, in this particular example, 4. Yes, so that means that, for example, for, let me use another color here, let's say green one. For this circle, there are 4 points within this circle, so we can say that they belong to the same cluster. Now, within this circle, there are also 4 points together, yes, so we have 4 points minimum achieved, so we can say that they belong to one cluster, yes. Now, one of these points is yellow. I will explain it right away why it is yellow. Because if we check the next point area, yes, so this one, you can see that this point no longer has at least 3 neighbors, or even 4 neighbors actually, yes. So that means, well, it's technically belonging to the cluster because it was belonging to the cluster in the previous sphere, but it has no new extra points to add to this cluster. So you can say that this C is actually border point, which specifies that your cluster actually ends here. Your red points are core points, which are inside of the cluster, and then green and then blue point is outlier points, which is outside of your cluster and has no common points. Yes, it doesn't. Well, if it was to have here one point which would belong to the cluster, then this point would also be yellow point. Yes, because it has a neighbor belonging to some cluster. But since it does not, well, then it's considered to be possibility in future if you add more points to belong to this cluster, or it may be considered to be belonging to some other cluster. Yes, so minimum distance here was 3, minimum number of neighbors was 3 actually here, not 4, but nevertheless. So okay, now as I said, the core points have to be directly reachable within this sphere epsilon range, yes, between all of the points, all of the combinations. Now, then we can say that point is density reachable, not really directly reachable from specific point P, if they chain, yes? So, for example, we can say that this point here is density reachable from this point, because they are not within the same range epsilon. Yes, you can see it here that our range epsilon here goes like this and here goes like this, and they don't overlap, but they do belong to the same cluster because of the neighbors who are reachable by each other. Yes, so they chain to each other. So that is the density reachable points. Now, outliers, as I said, are points that are not reachable by any neighbors to your cluster points. So there are also density connected points, yes, which are, well, accordingly considered for one point, like this. Let's say you have certain point, let me choose one. Well, this one belongs to this one belongs to this. Just let me see if I can find some point. Okay, yes, I can find some point, yes. Like, for example, this one, which belongs to this cluster, not cluster, but range, yes. And then here you have, no, actually not this one, but another one. It's too much circles, I am confused which I wanted to choose. Well, okay, let it be this point, yes, and this circle. Then these 2 points can be considered as density connected through let's say through this point, yes. So they are not not necessarily directly connected, so that's a little bit wrong. But they have one common point, so they connect to each other through intermediate point, yes, which are this and this density reachable, and this density reachable, but these 2 points, this one and this one, are density connected, whereas these ones were density reachable. So they are not directly reachable to each other, but they reach each other through another point, yes? And therefore, we can say that the cluster is the combination of the mutually density connected points. So all points that somehow reach each other through neighbors, through direct connections, anyway, yes, are considered to be belonging to cluster. And this stands also for these C points, which are also belonging to the cluster, but they are colored here in different color, just to show that this is where cluster ends. So the algorithm itself then can therefore be programmed somehow like this, not really sure which kind of language it is. It's some kind of pseudo language probably, but maybe not. At least it's not Python, not C, yes. And then we can say that the idea is quite simple. You go through each of the points and check if you have visited this point before. If you have, then you go to the next point. If you haven't, then you mark that you have visited this point now, and then you evaluate to which region, to which epsilon distance it actually belongs. Well, actually not exactly like that. More like this is like you simply take your point, like this, yes, say here you have that point, then you mark this region with the epsilon distance, and then you count how many neighbor points do you have within this region. So now I have 5. If this number 5 is not enough, less than this minimum specified, which you have to specify as a parameter in this algorithm, then you say that it's nothing, yes? It doesn't belong to any cluster. Now, if it is having enough points, then you consider which cluster it belongs to, yes, based on each neighbor iteratively, yes, and then you repeat this process for the next point, for the next point, for the next point, etc., etc. Now, it's quite complicated algorithm, yes, it consumes some time, but also not ridiculously intensive per computations or memory, yes. Again, it depends on the specific implementation, the fact that it can be made to run with this complexity doesn't necessarily mean that it will be run with this complexity, that sometimes it might be, for example, O of n square, as you can see here, but well, it's really about the specific implementation, yes. And the more data you have, data dimensions you have, yes, the more difficult it becomes, because, well, what we consider here is n, yes, what exactly was n? The number of points, I suppose, but if you have more dimension, then this goes more difficult, or n is number of dimensions, not really exactly sure. Okay. So let's go further to the matrix factorization problem. Why do we need to do stuff like that? What exactly example of this is? And actually, well, let me show you some example first, yes, and then we can understand better why do we need to perform this matrix factorization. So imagine that what we now are considering is some Netflix data we have collected, where you collect into database some, how it's called, ratings, yes, of the movies from different users. So you have user 1, user 2, user 3, user 4, user 5, and so on and so on. And then you have movie 1, movie 2, a movie 3, and so on. Supposedly, for each of these movies, each user is going to put its rating, grade, how it likes from in range from 1 to 5, let's say 5 stars or 1 star, yes, or maybe you skip that one altogether, so that the system then can try to recommend to that user something similar based on his likes or dislikes, in a sense, you can say. But the problem is that not all users even bother with putting these ratings. Yes, so in reality, it will look like some of the users have put like 5, let's say 5, let's say this put 5. Some of them really dislike the movie and they thought they have to let know about that fact, yes. But the majority of the data will be empty because people just watch the movie, they say, it's fine, nothing special, I'm not even going to bother to put some rating. And that's maybe most of the people. And you still have to somehow recommend to these people what they might like, yes, and that is a problem, especially if they don't say what they like, yes. So for that reason, you have to somehow try to predict how would user 5 would rate movie 2 based on his ratings and ratings of other users of other movies. So let's say it might have been rated by 4, maybe. We are not sure. And here, this user would have rated it as 3 or something like that, yes? But it's really difficult to do, especially if you have no data, yes? Now, this is similar to another kind of a problem. So we can represent the same problem in a different way. So let's say now I have a table of user 1, user 2, user 3, and movie 1, movie 2, movie 3. Now user 1 has rated movie 1, let's say 5 stars, movie 3, let's say 1 star. User 2 has rated movie 2 only and said it was okay, and user 3 hasn't rated anything, yes? So but he might have rated movie 4, for example, somewhere eventually there. So what we can see here is that you have a lot of missing values, yes? The fact is that, well, normally when we were working with some data set, let's say house prices, like where you had age, size, maybe something else, number of floors, you were having full data set and full features. But sometimes it happens so that for some house you don't even know when it was built. Yes, so in age you will have no data. And for some you might not know something else, yes? And that means effectively that for each example, for each user, there is a different set of features, different set of inputs. So for some users you will have 5 inputs, for some users you will have 10 inputs, yes? And you still have to somehow work with that. So this is a nice example of the dimensionality curves. Well, in our daily life, we can consider that dimensionality curves something like comparing small town to large megapolis like New York, let's say, for example, where it is difficult to find any information about some person, because if you live in some village, then, well, it's enough to know what is the name of that person, maybe some of his friends, and then you can find him easily. Now, in New York, you might need some much more data, like where he is working, maybe some region where he might live, maybe some places he visits, yes, and so on. So you have to have much more data to be able to predict the same thing in higher variation of data, yes, because in megapolis there are much more different people and much more options to be similar to your friend you want to try to find, but not exactly him, yes? Now, that is the problem, that you have more degrees of freedom than you have data, yes? Like more factors to consider than people. Just like, let's say, you try to say, sell 3 different houses, with certain list of parameters like age, like last renovation, like distance from the capital, how many bathrooms it has, does it have garage, what is size, and so on. So you can see already that we have 1, 2, 3, 4, 5, 6 parameters to estimate this house, and only 3 houses in total, which is very difficult, and that is the dimensionality problem. Yes, you have a lot of inputs to consider, but not enough data to even provide just as many of these. So in this kind of problems, we can use different approaches. Yes, first one is called feature engineering. Which is one of the steps which you normally have to take when you do any kind of problem for machine learning. So, for example, I can give you some task, yes, let's say, please find some data set and then use whatever method you like to get some estimates. So then you will have to consider, okay, I have found some data set, which exactly inputs do I need and which I do not. So you choose some columns of your table which you want to keep, and then others you remove. Maybe you decide to remove one of the columns because it has too much missing data and is not really useful at all. Yes? And maybe you decide to remove some of the columns based on the correlation analysis, like we did in one of our practical exercises when, if you recall, yes, we were considering that number of complaints was highly correlated for a user to the number of problems that were actually happening. Well, that's natural. If some problem exists, then the user will complain, yes, and these are related. So that means you can use only one of these features. Now, that is a really fancy word for saying which features you decide to keep and which to remove. Another approach is to use a regularization technique, which we are also familiar with, yes, that you try to penalize certain features for being too important to make them to be considered like not, well, more like common ones. Another approach is factorization, which we are discussing right now, which can help you to reduce number of dimensions as well, in a sense, yeah. But how exactly that works? Well, it's easier to show this example for the regular polynomials, like we learned in school. So let's say I have some polynomial p squared plus 2p plus 1, which I can now factorize into two smaller polynomials, p plus 1 and p plus 1. You do this by finding roots of this polynomial, yes, and then accordingly specifying them p minus p1 multiplied by p minus p2, where p1 and p2 are these roots. Now, same can be done for your data set as a matrix by factorizing it into two smaller matrices, yes? Like here. So here you have let's say, users as features and samples as, let's say, movies you want to evaluate. So then you split this one matrix, which is half empty, you can say, into two much smaller matrices. Now, first matrix has the same number of users. The second matrix has the same number of movies, but the number of movies for, well, the number of users who were actually rating every movie possible will be much smaller than total number of users. And likewise, majority of users will have some limited, or we can say latent, dimensions, movies they have selected to rate. So in a sense, then you can somehow avoid these zeros, this missing information, by splitting this matrix into two matrices. And then finding the matrix product multiplication of these two matrices is going to give you, well, maybe not exactly the original matrix, but something very similar to that, yes? And because it is going to be something similar, yes, that means that any missing values of your matrix S can be filled in with something, yes, because you don't necessarily have to produce exactly the same result for everything. You only need to produce the same result for actual data you have. I don't know, something like this. But whatever happens to the next ones is not so important to this matrix because there is no data. It is important, however, to make the correct predictions and good recommendations. That's another aspect, that's another cost function to discuss and stuff like that. But at the very least, we now have the freedom to make this kind of prediction. Yes, because, well, this user haven't had predicted anything for the last movie, but it is going to calculate some numbers for this user based on this matrix product, and he will have some pseudo rating he might put for that kind of movie based on his preferences and based on other users' reviews. Yes, so that is the idea. Of course, it's quite complicated to do. Yes, it's not as simple as to describe. Okay, like here it was. Step 1, step 2, and step 3 to make this matrix factorization. This is actually optimization procedure. So you try one matrix, you don't like it, you change it, you try another, and again, moving multiple iterations, just like we did with the well, neural networks. So instead of training the connections between neurons, now what we do is we train for these matrices. You don't like one matrix, you take another. You don't like this, you take next one. Yes, so that's what you optimize these matrices. Now, again, the main goal of this was to fill somehow these otherwise unknown, unfamiliar data zeros, yes, some observations that were missing. And what we try to do is to minimize the, well, basically square error, yes, the level 2 regularization, that is for square, for any values that you actually have. So for those ratings that users have provided, you want this model to work as accurately as possible, whereas for those ratings that were not provided by users, you don't know, yes? So you assume that they would have rated like this, but the goal is to keep the correct answers for the data that was actually there, yes? So for those ratings users have, it has to stay the same. Now, we can even use gradient descent method for this kind of problem, except that this time we are now dealing with matrices, yes? Now you have matrix products, and you need to calculate gradients for these matrices as well, which is, again, nothing too crazy, because we did that, yes? In neural network we represent all the connection also as a matrix, yes? And we did calculate gradient for this matrix, so nothing too crazy, but it's a difficult mathematical topic, yes? Now, here, what I wanted to mention is that there can be different methods which you can use to run matrix factorization. One of these methods is called Markov chain Monte Carlo method, yes? So this is basically like an algorithm which you can use to calculate this factorization, just like numerical integration can happen with rectangles or triangles or other shapes, yes? Or even some more advanced techniques. So this is basically specific implementation of this procedure. How exactly you are doing this factorization? Just like, I don't know, how exactly are you calculating roots of the square equation? Do you use formula? Do you use numerical methods? Etc., etc. Yes? Now, this method is probably considered like the most accurate one right now, yes? Again, based on this information of this lecturer. Now there is another method as well, alternating least squares method, which works differently, but the problem is it's quite computationally demanding. It's asking a lot of time to perform this thing, just because, well, it takes all of these matrices and calculates the cost functions for all the possible combinations, and it's just too many calculations to be done. It's like a little bit straightforward approach, not really smart, yes, because some of the calculations you might not even need to do, yes, and this does all of them regardless. Now, SGD also is one of the methods you can use for this factorization, yes, so this is first method, second method, and another method, yes. And specifically for the Netflix case, I have already shown you this example problem they have with different users and different movies, and not every users provide every rating for each movie, and what they want to do is to still make accurate recommendations for users what they want to search. And here is some ongoing research actually where we use different algorithms, yes, and have seen how well it performs. So the higher number here is better, yes, so you can think of this as an accuracy, yes. Now, let's then conclude with the performance aspects, yes. Now, what exactly can affect how fast you can get the solution? First of all is how many data do you have. That always is the issue. The more data you have, the more time it's going to need. But the problem is some of the algorithms are depending on the data, maybe even linearly, well, although there is very few of these algorithms. So let's say you increase the amount of data 5 times, and also you will have to spend 5 times more time. But the majority is non-linear, like this one, for example. So if you increase the number of data 5 times, you will have to spend 25 times more time than before. Or maybe even, like we have seen here, you had the third degree. Yes? Now, K is the number of clusters here, which is not that big issue, but still, the more clusters you're trying to search, it goes exponentially to the third degree. Now, there can be also some less strict, more friendly, we can say, cases, yes, like this one, actually is quite good, because it looks almost linear. Almost. It's not exactly linear, yes, so, but will look like this. So, for example, fast Fourier transform FFT also is of this type. Yes, it has actually even n of log 2n, like this. Yes. If you increase the zoom here, you will see that this line actually moves somewhat a little bit like curved, not exactly straight, but this curvature radius is very, very large, and it almost looks like a straight line. This is actually quite good, yes, remarkable, we can even say. Now, that is the first issue, to consider the amount of data. And the second issue is, of course, model size. The more complex model you have, the longer it's going to take. So that was an example of the practical exercise 4, I believe, which I gave you to do yourself, because there even are no individual parameters for you, yes, so no really point to spend too much time on it, yes. And there you had chance to analyze neural network with one hidden layer, with 2 hidden layers, and it's difficult to see from that example that the second neural network is going to take longer to train, but obviously it happens, yes? In our case of unsupervised machine learning, the model size is depending on the number of clusters. How many clusters do you want to find, yes? Now, there is also something called long-tailed models, yes? This is for the kind of a distribution being used, like in probability theory. You may recall we also discussed Pareto distribution, some other log normal distribution that are having these long tails. Yes. So what is the problem with this kind of a distribution is that it is still highly possible to get a very remarkable difference. Yes. So, for example, this is for the Pareto or similar distribution, yes, and this is like a normal distribution. So, if you compare, let's say, the height of a person, yes, so 1.5 meters, 2 meters, and so on. So there are somewhat limited outcomes. Yes, I don't really honestly know what is the minimum record small person in the world and what is the maximum, but I can for certain say there is no person who is 3 meters, 10 meters, etc., etc. Just such people don't really exist. Whereas if we consider, for example, how rich is the person, then of course there can be people with negative balance, yes, very high negative balance, and there can be also billionaires. Yes, yes, there are very, very few of them, but the difference is very, very large. Yes, the majority of people will be, well, somewhat wealthy. We can say that they can afford to travel, they can afford to buy something for themselves and all that stuff. Yes, they are not really rich, maybe, but they can live nice and comfortable life. Yes, again, we can consider about how much is that money you need to consider, but there are also, of course, a lot of poor people in the world, but there is very, very few of the rich people who are different in many, 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 many magnitudes. Like if we say, for example, here we can say about 5,000 per month, like very, very good income, yes, for Europe. And then they have like millions per month, yes, which is way too high. Just like if we compare the height of the person, let's say the normal height would be 1.7 meters, and there someone would be 10 kilometers height of person, which is just impossible, naturally, yes, but statistically the probability is almost zero for that to happen. And here it's not, because this distribution has this long tail which does not cancel out this possibility. It's even possible that somewhere in future there will be trillionaires, yes? It's just probability-wise not happened yet, yes? So that's what is the problem with these long tail data, long tail distributions, and so on. Now, also there is one more important aspect to consider, which we will discuss more in the next lecture, because this one is closing almost, yes, is the mode of operation. So we can have offline mode and online mode. What is the difference? So the difference is that in offline mode, that's how we usually train our model, but it can also operate in this offline mode. You have some server which, let's say, collects some data, I don't know, from network, from sensors, from anything, stores this in a file. Then you take this file to another computer, train a model there, take the model, take the file to another much smaller computer, maybe some Raspberry, yes, and run it there when you need. But it's not exactly like you need to make immediate decision to actually do something. Yes, it has to sometimes process some data. Let's say you have accumulated some temperature measurements over over an entire day, yes, and let's say once per week you send this week data to this Raspberry Pi to do some data analysis on your temperature measurement. So that is offline mode. Your model doesn't necessarily have to provide you answer immediately. Yes, you can wait. You can wait day, you can wait month, you can wait week, depending on your problem and situation, but it's not a principal question. Now, in online mode prediction, it's very critical that your model produces your prediction right away, as soon as possible. We can mention some autopilots here, yes, or well, also autonomous cars, yes, and also related to these autonomous cars, city infrastructure like traffic lights and all that stuff that has to consider how many traffic is there, how many pedestrians are waiting for the green light, yes, etc. So these has to be done in the real-time mode, or as close to the real time as possible. Yes, we'll consider and discuss online model prediction and even online model training, because, well, ideally what you want to do is, after you have trained some model, you want it to be better in the process, yes, so you continue to train it as you use, so that also requires to use online prediction. And of course, for this kind of problem, they have to provide more resources than for this. You can use, I don't know, very old PC for this kind of problem. Say, it's going to train your neural network for 1 week, but okay, I don't care, when it will be ready, I will use it. Or, like, if you really need to have it fast, then you will have to have much more computationally efficient system, yes? Now, we can improve how fast our training and operation does by 3 different methods. First one, you can improve the algorithm itself. You can use more efficient algorithms, you can use better stochastic gradient descent method instead of a regular gradient descent method, etc., etc. Yes, just like we discussed here about these matrix factorizations, stochastic gradient, MC, ALS, and others as well, yes, so you choose whichever is better. And usually this doesn't come with any significant costs. Yes, you have to spend time, you have to choose different algorithms, but otherwise it's not financially intensive, yes. Now, computational improvements, you can try to optimize your code to run faster. You can maybe, considering, let's say, your system has GPU in it, but you didn't use it, yes, consider rewriting your code to actually include GPU processing in your program. And in this case, we speak that you already have this hardware, but you are just not utilizing it the most efficient way. Let's say you have some very powerful processor, but your code only uses 1 core of your processor. So you want to make your program run on multiple cores instead of that. Yes, again, this is certainty free. And scale up is basically when you try, let's say, okay, I'm not going to use one very big server to run my problem on it. Instead, I'm going to distribute my problem around different places. And that's how that's done in modern life. For example, in United Kingdom, in Manchester, yes, there are traffic lights that consider number of pedestrians waiting for the green light. And in each this traffic light controller, yes, when you see red, green or yellow, there is inside a small computer which contributes to the total edge cloud, and therefore if you decide to add more streets to this system, you will have no problems that, okay, you had, let's say, 10 intersections to work with, now you will have 100 intersections to work with the same system. And it's not going to handle this amount of data anymore. But if each of these intersections also contributes its own computer resources to it, then you can easily scale it. Yes, that's it about it. You can split your problem into smaller parts and process it but by fractions. But then again, there comes problem that you will have to transmit data from one system to another system. That can be a bottleneck for network, which is again something you can try to improve by improving topology of network, the protocols, maybe going from 4G to 5G, like was in the case of Manchester that helped them. So basically, that's how you can try to solve this kind of problem. And today, this concludes our lecture. So we discussed some clustering algorithms. One of the groups will have this as practical exercise today, another will have next week, and next week we'll consider to discuss how exactly we can adapt neural networks, how this transforms into ChatGPT, yes, and also we'll discuss additional method which is not supervised and not unsupervised. This is called reinforcement learning, that works slightly differently from both of these methods. So that's something to discuss for us next week. But today, thank you for attention. If you have any questions, don't hesitate, and see you then when we meet again.